Morning.
Hello, audible.
Yes.
Yesterday we seen the RLCD circuit. Similarly, this RC circuit. Okay.
Sir, there is a little noise in your voice.
Hello. Yeah.
Sir, there is a little noise from in your voice, sir.
Okay. Now. Maybe yes to some. Here also, see this. If we draw the impedance diagram for this is your resistance, and here it is negative. This side reactance. Okay. This is XC. Then this is your impedance. This is the angle is phi. Okay. So, like this. This is Z. Then again, impedance is under root real part plus imaginary part, because Z here we write R, sorry, yeah, minus JXC. Okay. And here with inductive reactance, Z equals to R plus JXL. XL is plus, X is minus. Okay, please you remember.
सर आपका वॉइस क्लियर नहीं है.
Just a minute. Now okay. Hello, audible?
Yes, sir.
Yes, sir.
Yes sir.
Thank you. Then current power factor, we can, here it is leading the power factor, here it is lagging. Okay. These things we can calculate. Now here, because here angle is negative. Now if you take an example of this all, means RLC in series, then it means resistance in, now if voltages we write now this vector diagram for this, current is common na here, same. This is the current I. Now voltage across R drop, it is in phase with current. This is the phase with current. This is your VR, because it is IR, no? VR equals to IR. Okay. Now due to this L, this is your drop perpendicular to this resistance. Okay. This is your VL, and here it is VC. These are opposite. Now it depends what is the value of here capacitive reactance and inductive reactance. It depends. Okay.
Sir, again your voice is not clear.
The voice is clear. I think the issue from her side.
Internet issue. You are attending the class on mobile or what? Internet. You check the internet level at your end. Just 1 minute, please. Hello, now audible? Yeah. So see, these are opposite and equal, that depend. Generally, such inductive is higher than capacitive reactance. Okay. So if we subtract this portion, because they are opposite, vector sum if we do, then see, this is equals to, suppose this portion. So if we subtract the here, it is VL minus VC vector, differential vector, and this is then this VR plus this this will give you total voltage. Okay, this portion is this. Okay, so now if you calculate now vector, so it is VR total voltage. This is equals to VR plus VL minus VC vector sum. Now this is IZ total impedance into current. This is IR plus this is IXL minus IXC. This all are vector sum. Vector. Now I, if you take a common, then I cancel, then Z equals to R plus, either you take a vector or we can write in a rectangular form. It is XL minus XC. Please, XL minus XC means net reactance of circuit. If we draw the reactance impedance triangle, impedance diagram, phasor, like this. Hello, this is your inductive reactance. This is your negative XC. Okay. Now their difference is here. This is called XL minus C equals to X net reactance. Okay. Then this is your Z total. Z. Then this is your phi. Okay. This is your, so that's why this is your impedance. Now you can, if we calculate mode magnitude, then it is under root of real part square plus XL minus XC whole square. Okay. This is the impedance for RLC series circuit. Okay. Now it depends which is greater. Okay. Suppose the reactance portion is high, this, then this diagram will be, now actually this RLC series circuit can be operated. See, RL always lagging, RC always leading. But this RLC series circuit may be operated lagging, second leading, or it can maybe also operate at zero power factor. Unity power factor. Okay, how it is? Suppose in this condition, this is when inductive reactance is high, which means XL value. Then it is lagging because net reactance is positive, correct? No? This is positive side, no? Because in the coordinate this is 0 port, so this is negative, this is positive side. But if XL is more, maybe your inductive reactance is more. It depends on frequency. Okay, because XL equals to omega, and omega is frequency in radian per second. Okay, or we can write 2 pi f. Omega means, hello, this is 2 pi f actually. Here f is frequency. Hello, f is also frequency, but it is in cycle per second, or it is called hertz. Clear? So XL equals to omega L. Now it depends on the frequency. Generally na, at higher frequency, at high frequency, because if frequency is high means your inductive reactance is high, but x equals to 1 by omega c, or it is 1 by 2 pi f c. Now if high frequency, this will low. So depends on frequency, what frequency you apply here, 50 hertz or megahertz or kilohertz. So their value are changed, which XL, XC. So your circuit behavior is also changed. Circuit behavior also change. It means at higher frequencies, it is at this is at higher frequency, high frequency. This is at low frequency, because at low frequency your inductive reactance is low, but capacitive reactance is high. Low frequencies is we operate now. Or this is at resonant frequency, or at resonance, or you can write under resonance condition, it is operate at unity power factor. See this resonance also in your syllabus, okay? Resonance circuit. This lagging we have explained, but when your lower frequencies, this will be high. If frequency is low means this value is high. Okay. So if your XC is greater than XL means in that condition now your this diagram is this is R. Then XC part is more. If XC, then and this is your XL, then it means this part we subtract here. This portion goes to this. Then your net reactance is XL minus XC. So it comes negative, no? This value is high. Then this is your Z total. This is Z. Okay. So now angle is negative. Here it is angle is positive. This clockwise direction. This is negative angle. It means power factor is, so here leading power factor. Okay, in this case. Got it. Now at unity power factor now, it means this is your resistance of circuit. Resistance is not change on frequency. It not depends on frequency. Only XL XC
माइनस XL नहीं आएगा?
देखिए इट इज ए वेक्टरल डिफरेंस. आप XL XC लिखेंगे वो सेम आएगा. नेगेटिव आएगा ना, तो नेगेटिव भी स्क्वायर तो पॉजिटिव ही होता है. Z is always R square minus R square plus XL. Generally we write this only. If this part is high, then it negative. Negative square is also positive. Okay. And vectoral difference is not we take like we are not subtract from higher to low. This is always we kept this fixed XL minus XC. If XC is high, it means it is negative value. Okay, that's why ना.
सर अगर फ्रीक्वेंसी हाई होगा तो लैगिंग हो जाएगा क्या, और लो होगा तो लीडिंग हो जाएगा, ऐसा होता है क्या?
Yes.
मतलब एक कांस्टेंट, मतलब एक पर्टिकुलर सर्किट में अगर फ्रीक्वेंसी हम बढ़ा देंगे तो वो लैगिंग में आ जाएगा.
हाँ, सर्किट का बिहेव चेंज होगा. ये इफ यू वेरी द फ्रीक्वेंसी, तो समटाइम ना वी वेरी फ्रीक्वेंसी इफ वी चेंज द ऑपरेटिंग मींस बिहेवियर सर्किट, और आइदर ना you fix the frequency. we take this, and actually generally na LE we cannot make variable. Capacitor
ये जो 50
capacitor
हर्ट्ज 60 हर्ट्ज होता है, 50 हर्ट्ज और 60 हर्ट्ज के अगर हम चेंज कर रहे हैं 50 से
सब
60
चेंज
हर्ट्ज।
नहीं होगा, इट इज इन किलो हर्ट्ज मेगा हर्ट्ज में चेंज होता है।
ओके ओके ओके, थैंक यू।
So either we can change by vary the capacitor value. You fix the frequency, but we change the capacitor. Then also it is possible to get the resonant condition, or change the lagging leading.
थैंक यू सर।
Now see, if I am telling this third condition, in that now what happened? This is the R, but here now at some particular frequency, under that condition now this both inductive reactance and capacitive reactance are equal, XL and XC. It may be possible both are equal, then your XL minus XC is 0, means the difference is 0. Then Z equals to R only in that case, because under this condition Z total impedance R square plus XL minus XC. This is 0. If this is 0, then under root R square, it means it is R only. Okay. So under resonance, please, it is very important. I here cover the resonance condition also. That is called resonance in series circuit, RLC series circuit. Okay. So under, now we are discussing this under resonance condition. Impedance is only circuit impedance. Total impedance of circuit is only R. It means they are there physically, means virtually they become 0 because they cancel each other effect, XL, XC. They are equal in and opposite. So they cancel their effect. Only your circuit is behave like a pure resistive circuit. Then you can calculate power factor cos phi. That is R by Z, na? But here R is also Z, R by R. It is 1. Unity power factor. 1. Unity, 1. Okay. So it is possible there is a RLC series circuit, but it behave like a pure resistive circuit, pure resistance. Because unity power factor is only in case of resistive circuit only. So under resonance, your series RLC circuit become a pure resistive circuit like. Okay. This is very important. Now if you draw their voltage diagram, this is your VR, and your drop across L and C. This drops VL, okay, and VC. They are equal and opposite. Then if you calculate the total voltage, this total voltage is appear across resistance only, source voltage. Hello, in circuit this applied voltage is equal to this only because they are opposite and equal. But they are there, means high, the voltage magnification take place. In resonant condition, if you calculate current, if you calculate current equals to total applied voltage by total impedance of circuit. Voltage, applied voltage, impedance is R only. So see, impedance is reduced, the current is maximum. Under resonance, current is maximum. and Z is minimum. Please remember, in series resonance circuit, this is minimum, this is maximum, current is maximum. Okay. So I brief also because numerical on resonance also, so I brief this. Now you come to the resonance. What is the resonance? Resonance. Okay. So this resonance is nothing. Resonance in AC circuit. AC circuit. Resonance. It is a condition actually. Condition at which your inductive reactance equals to capacitive reactance, or net reactance. Net reactance is XL minus XC is become 0. Net reactance of circuit reactance or imaginary part, like we write na Z R plus J XL minus XC. This J is imaginary portion, so this becomes 0. Okay, got it? This is the condition at which resonance. Now this condition maybe like your RLC circuit or series, we can connect in series or parallel. So there is a AC circuit also, parallel circuit also, no? So resonance circuit. Series resonance, parallel resonance. When it is occurs in a RLC series circuit, okay, R, L, and C, suppose. So now if it is occurs in a series RLC circuit, okay, parallel resonance. So please, in parallel resonance means your all component R, L, and C are all connected in parallel. So like this form a parallel RLC circuit. Okay, resonances can occur in this also R, L, C. Okay, if you pure resistor, pure inductor, pure capacitor you connect. Now actually what happened na, this capacitor we can actually na, this R is not externally, sometimes this is a coil. This is a coil, practical coil, it is a equivalent circuit. Suppose a coil is connected with a capacitor. This coil has a resistance and inductance actually, practical coil. Okay, so this form a resonance. Okay, series resonance. Similarly, actually series resonance circuit na, there is a means we can say like there is a resistance of practical coil in series with the inductor, and your capacitor is pure. Okay. This also form a resonance circuit, and now they are connected in parallel. Okay, if you are this is the coil resistance inductor. Okay, this form a your either this, we can make it as vertical circuit. Okay, like this inductor, resistance, inductor, then here C. So this form actually parallel resonance. It is the same like we connect. Okay, simply you can say like here you apply the voltage like this. Okay, this. Okay, or either we can show like this. So your total voltage is applied across this. Then this is the total current. Then this current is divided in these two paths. Okay, parallel path. Here is also same. Okay, this is the CLR. Okay, now parallel circuit is also called as a tuned circuit or tank circuit. Now if you if you connect a pure inductor with pure capacitor, this is it is called tank circuit or twin circuit. Okay, this also form a your parallel resonance. Okay, this is a parallel. It is called tank circuit or twin circuit. Okay, parallel resonance circuit is called tank circuit or twin circuit. But actually, pure inductor is not possible. Pure inductor is, that's why therefore there is a resistance we consider. Resistance with inductor, and this is your capacitor. Okay, my dear. So this circuit we consider as a parallel resonance. Okay. Now you can draw it horizontal, then it is like this. Okay. Please do not confuse, the circuit is same. Okay, please. This. Okay. So this is generally in parallel resonance, this circuit we use. Okay, this. Either all three in parallel, or either pure, or either this. Now it is clear. Okay. So generally parallel resonance is this. Okay, parallel resonance is this. This is the parallel resonance. Okay, RLC means this resonance condition is occurs in parallel circuit. Then it is called a parallel resonance. This is your series resonance. Okay, clear? But their opposite, their properties are opposite. Under resonance, no, in series resonance, impedance is at resonance condition, series resonance circuit. Okay, Z is infinity. Sorry, Z is maximum, current is minimum. But here it is opposite. Their impedance is low, current is, sorry, here we wrote wrong. Impedance is minimum, current is maximum. But here it is impedance is high. Dynamic impedance. Okay, current is low. They are opposite some properties. Okay, here parallel and series resonance. Okay, their difference is also asked in your exam. Let us go on the questions, please. Now it is a good idea, na? Actually, see, if we yesterday's lecture I not explain this basic, then you not get this idea, this parallel series. Then it is like a rectification. You just memorize the question solutions. These things are required. That's why. Okay. Suppose in engineering days you are not take it serious, and now you can take at least. Okay. That's why.
Thank you. I don't always I am try to we just only solve the numericals, not explain, but it's not this numerical we also solve. Okay, not issue, but I saw the resonance circuit. See, this is Compare the series and parallel resonance circuit. Find resonance, frequency at which this circuit is resonance. This circuit. Okay. Then what is the meant by resonance in RLC circuit? Compare series parallel resonance. And same question is this. Part B means this part. This circuit there here also. Okay. Got it? Same. Now here also. This question is also from this. I take these two questions. These two questions given. See now. Okay, readable. What is the meant by resonance? Resonance is a condition at which your net reactance becomes zero. Then XL equals to XC. Then okay, that is called resonance. Now series and parallel resonance. Okay. There was a one. I put comparison on the group. It is given in basic notes also. Which time, which no. Image. Okay. Okay, I will share again. Just a minute, please. Okay, I will share it later on. Difference in this. It is there. Anyone has this?
Excuse me, sir. Which answer you are looking for, sir?
This comparison. Compare with the series parallel.
Sir, I have, but I will share after some time in the group.
एक्चुअली मैं उसका स्क्रीनशॉट लेके रखा था, पता नहीं कहाँ से। जस्ट मिला था। मेरे फाइल में वो था। निकल गया उसमें। यस, मिल गया। तो ये तो बहुत पैरेलल है। और ग्रुप में डालते हैं, हो जाता है। ये है क्या? एक मिनट।
मैंने डाल दिया सर ग्रुप पे।
हाँ हाँ ये मिला। नाम में रह गया तो फिर दिक्कत है। Okay, here I put a see. If we read the comparison, you take the in group. Okay. See, in series resonance, it is a acceptor circuit. Series resonance. Why? Because it accept the under resonance. It accept more and more current, means high current. But parallel resonance is called as a rejector circuit because it impedance is high at resonance in parallel. Then it reject the current. It accepts the current, series resonance. Second, at resonance, impedance is equals to resistance only. But at resonance, impedance is maximum nearly equal. It is infinity in parallel. That's why current is low. Then in parallel resonance, current is maximum. That is V by R. I equals to. But here V equals to effective resistance, dynamic impedance. That I will L by CR. It is dynamic impedance. I will show you. Series resonance, the power factor is unity. Parallel resonance is power factor is unity. Both has a unity power factor. But current is different and impedance is different. Okay. Now series resonance, voltage magnifies the voltage across inductor and capacitor. But in parallel resonance, magnification is it magnifies the current, not voltage. Parallel. So this is the comparison, please. Okay. Yes. Yes. So this is the difference in this, please. Now we come to the solution of this, numerical. Find the frequency at resonance. Okay, so here it is the circuit it is shown. Here we apply the potential, because now it is a series circuit. Okay, now if you apply voltage and frequency here, is AC voltage. So actually, basically, if this now first in our case, it is a series resonance. Now in our series resonance, this is the resistance, this is inductor, and this is a capacitive resistance. R, L, C. Now equivalent this. Now we calculate their XL, XC also. Okay, this omega L. This is 1 by omega C. Now at resonance, XL equals to XC, or it is omega L equals to 1 by omega C. This is occurs at a resonant at a particular frequency. These are equal become. Then it is we denote by omega naught, means resonant frequency. Now omega we take this side now, then it become omega square equals to 1 by LC, or omega naught equals to, if you do na, it comes 1 by under root, because one root is 1, but it is LC. Hello. This is your frequency of resonant, but it is in radian per second, okay? Resonant frequency. Now omega, you know, it is a 2 pi f naught equals to 1 by under root LC, or therefore frequency at resonance, or it is called resonant frequency. Resonant frequency, okay? Resonant frequency means frequency at which your RLC circuit is resonant. It means it comes under resonance, okay? It is F naught equals to 1 by 2 pi under root LC. Please listen. This is for series RLC circuit, okay? So this is the formula for resonant frequency. Resonant frequency it is a particular frequency at which resonance is occurred. Means this circuit is start operate at unity power factor. Okay. So like this circuit, actually here so this is a coil which has a resistance and inductance. Means there is a coil which has a resistance and inductance. Then there is a capacitor. Then again another coil which has an inductance and resistance. So there is a coil resistance and coil inductor. Then they give the pure, means these capacitors are pure. This is your coil 1, 2. So this is given R1, this is given L1, this is C1, this is now L2, R2. This is C2. Now this all are in series. Now let us make this like. Now if you apply here potential. Okay. So first we calculate the total, because there is a 2 resistance in series, 2 inductor in series, 2 capacitor in series. Okay. So you have to find their equivalent. Now series in parallel, I will also explain this. If 2 resistance in series, hello, then suppose R1, R2, then total resistance R equals to in series R1 plus R2. If 2 resistance in parallel, please R1, R2, then R equals to R1, R2 by R1 plus R2. Okay, like this. Okay, same like if inductor के case में. Okay, hello, please. But there is a see, suppose 2 coils, 2 coils, and this coil 1, coil 2. They have a self inductance L1, L2. Now if they are connecting series like this, sometime there is a mutual inductance is also there between 2. Then it is like M. M is the mutual inductance. M is equals to, it is nothing but it is K root of L1, L2. K is the coefficient of coupling factor. If 100% couple K equals to 1, means the entire flux produced by L1 is linked with L2, and the flux by L2 is linked with this. Okay, please, this is mutual inductance. What is it? Mutual. 10. Okay. So now the total is in series, na? It is L equals to L1 plus L2 plus minus 2M, means it is double mutual inductance. If mutual inductance is not, the coils are, the flux is not linked to each other, then it is not there. It comes no here, only this. But if there is a mutual inductance between this, then it is plus minus 2M, not either or plus or minus. See in which case it comes plus. Suppose current, there is a dot rule in coil. Suppose at this is the dot, this is your dot. If you take a coil, there is a dot. It means if current is entering both coils at the dot, then it is plus. Means their flux are in same direction, both. Flux produced by coil 1 and coil 2 are in both. Okay, then it is. When it comes negative, na, suppose this is the coil 1, this is coil 2. Suppose the dot is here and dot is here. Now suppose it is connected. This is also in series, na? This kind. If we connect this way, hello, and you apply the voltage here. Here we apply like this. So see here what happens. The current, if you apply, this is positive, this is negative. The current is enter here in this coil 1 dot, but here it is exit. Then mutual inductance between these two is M, L1, L2. In that case, na, it comes negative. Clear? Okay. That's why na, in transformer and motor, 3-phase winding, means 3 coils are there. Okay. When we make a delta star, na, there may be a dot. Okay. That's why na, their terminal is like U1, V1, W1, or this is U2, V2, W2. This marking is very important in motor and generator. Okay. It is, otherwise, there if dot means if there is a coil has a polarity. Otherwise, no resultant magnetic field produced in air gap. Then this motor will not rotate sometime. Okay, the torque is, we not get a torque, constant torque. Same like in transformer, the voltage is not induced because they oppose the flux produced by 1 and 2. That's why this important, this what terminal identification. We fix the terminal, then we connect. Either we connect short, means in star or delta. Got it? Due to this only. Okay. So you know how we calculate the series if inductor are in series and parallel. For parallel, na, this also same like a resistance. Hello. For parallel, it is, you know, for parallel 1 by R equals to 1 by R1 plus 1 by R2. Here it is 1 by L equals to 1 by L1 plus 1 by L2. If mutual inductance, then again plus minus 1 by 2L, like this. If it is not there in parallel, then it comes no come in the mutual inductance. Okay. It is like a resistance only. So there is no confusion in inductor. But in capacitor, na, if
Sir, in inductor, if
yes.
Sir, in inductor, if the hello.
I am listening. Tell me.
Sir, if inductor, the dot or one is current is in and another is current is out, then only 2M is minus only, na?
Yes. अब ये देखिए क्यों इम्पोर्टेंट है, इसमें टाइम लगता है, लेकिन आप लोगों को अगर इफ यू आर इंटरेस्टेड आई एक्सप्लेन प्लीज. पता चलेगा नहीं तो कि सर तो टाइम पास कर रहे हैं, न्यूमेरिकल तो सोल्व नहीं कर रहे. इट इज नॉट लाइक दैट. आई कैन एक्सप्लेन. हेलो.
Yes, sir.
सी अभी
Yes,
देखिए
sir, please
आपका
explain numerical we can crack after this.
What?
Sir, please explain this. If we know this theory, then numerical will be easy to solve.
हाँ, thank you. Now, see, अभी आपका जो मोटर का कोर है, 3-phase इंडक्शन मोटर का एग्जांपल लेते हैं. We are taking example of 3-phase motor. There are 3 coils, but उसका जो आयरन कोर है, it is same ना. Or then if you cut that and suppose we take this is your iron core, okay, iron core, soft iron core है. There are 3 coils are wound on this. See, like this. This is coil 1. They are same na, identical. Coil 1, coil 2. Okay, like this. Okay. Second also here. Like this. Now this coil, how we connect this? It depends. If you take an example of only 2 coils. So suppose there is a dot here and dot here. Now if we connect in this coil, these 2 coils, like this is now become series na, and here we apply the first positive, suppose voltage means when sinusoidal it is plus wave, okay, first instant. So see, current is start to flow here, then see, it is like this, then it comes, it enter to this coil, again. So see, flux produced by this coil is, what is the direction? You please apply the right hand thumb rule. If current is circulatory, flux is straight. So the flux produced by this coil, just a minute. The flux produced by this coil, it is come to this side, na? It is this side, na? Here, okay. In this core, it is exit and it will enter to this entire like this, na? So here it is exit. This. Suppose this is coil 1, the flux produced by this, the coil 1, the flux produced is in this direction, phi 1. Okay. Now the flux produced by this also in the, if current is in this direction, in same direction, this is phi 2. So see, this both flux are in same direction. So it will aid na, total flux in the core is aid now. Correct? Okay, that's why in that case na, means L1, L2, here mutual inductance. The flux produced by this, it is linked this, and the flux produced by this also linked, because it come na, and again return to this. So both coil are additive in nature, support each other flux. It is aid. Total link flux linkage is high. Okay. In that case na, it comes L1 plus L2 plus is 2m. If there is a mutual inductance, it means, so it is support. Now now if you change the polarity na, like now suppose this is your V1 terminal, this is V2. Okay, now this is the second coil na, U. This is your U1, U2. और सपोज कॉइल ए, हम इसको सिंपल कर सकते हैं, कॉइल ए कॉइल बी है. सपोज दिस इज द कॉइल ए, दिस इज कॉइल बी. द कॉइल ए, इट इज A1, दिस इज A2 terminal, this is B1, B2 terminal. Now suppose we connect like this, and here it is the coil. Okay, now here current direction is changed, it is now like this. Okay, please. It is now this direction. Now, if current is in this direction, the phi 2 is in opposite direction like this. So you know, sorry. In this case, what is the net flux in the core? They are in opposite, na? This flux is in opposite direction, phi 2.
and this phi1 is in this, so they cancel. Then now net flux is 0 if coils are identical. Clear? Okay. So in case of motor, there is a 3 coils A, B, C. Now that's why if we connect in a star or delta, their polarity is very important, so that their flux is aid. Then we get a resultant flux, constant value. Okay. Same like in transformer. Suppose like in there is a 3 coils now generally in star this is A2, this is B2, this is C2 in transformer, or it is this is A1, this is A2, this is A3. Okay. When it is manufactured, then we determine the polarity and we fix, we name this terminal. Then if we connect 9 star, then we short this and we apply the here voltage here. Okay. Then their flux are in at like this way. Okay. In 3 phase, phi 1, phi 2, phi 3. Then we get their vector sum. That's why we get in motor it is a total resultant flux equals to 1.5 times of maximum flux per phase. It is a constant always. But if you suppose one coil is opposite, if you take a one coil is opposite, means by mistakenly this is A1 and this is your A1, B1, C1. Suppose by mistakenly this is A2. This become A2 and this is A1. Now here it is no opposite phi 1, suppose flux produced by this phi 1, this is phi 2, this is phi 3. Okay, so this will be your in this direction, it opposite. Now their vector sum is not constant value, it is different. Their phasor is changed. That's why it is very important, your terminal identification. By series lamp we can check how we identify the terminal of a motor or transformer. Either you have a inductance meter or either a series test lamp, you can easily see. Okay, series test lamps like there is a 3 coils. We not know which is A1, A2, B1, B2. Then how we are transfer? Very simple. It is like this, all 3 are on same core. We represent this by this way. Like. So see, first across first coil we apply 110 volt, D. Okay, here AC, 110 volt AC. And these 2 coils we connect any 2 coils. Continuity we can check हमको ये पता चल जाएगा कि ये दो this 2 terminal of this coil A, this 2 terminal of coil B, this 2 terminals of coil C, coil C. This we can easily find by continuity meter. On motor terminal coils are inside, but the terminals are here. Okay. Now by checking the continuity we can know this is coil 1 terminal. This is coil A, this is coil B, this is coil C terminal. Continuity से पता चला सकते हैं हम. Okay?
Yes sir, yes sir.
But हमको ये पता नहीं है कि this is A1 or this is A2 or vice versa. Okay? That we find. How we can find? See, we apply the okay. in any suppose C is coil, we have to apply the potential here, but 110 only, not 220. Why? Suppose, tell me. And now we take a and we connect this the remaining two coils terminal like this, and we apply the potential across this coil C. Okay, like this. Okay. Then what happens? Now we short this and we connect one lamp here. Please. Now it depends. It is bright or not bright. Hello. It means oh sorry. ये दो के across ना potential apply करेंगे and lamp is put across this. Sorry. Suppose one lamp is put across this coil C. Okay, like this. Okay, please. We short this and we apply the potential and we one lamp is put like this. Okay. Now what happen here practically? See, these two coils are connected across supply. Then there is a flux is produced. Now, if suppose both flux are support, then in the core there is a double flux. This both phi1, phi2 is linked with C coil. This phi1 plus phi2. Then there is a EMF is induced in the coil C. The lamp is bright, more bright. It is bright. It means this part and this part are dot. We can say, sorry, this part or this part is dot, means they are support. Then we can find their terminals are okay. This is your A1 and this is your B1 terminal. We can give the name then if bright. But if suppose their flux are opposite, the coil one means they are this and this are opposed. Then net flux in the core is if the phi1 minus phi2 means it is very negligible or not G. It is no EMF is induced in the coil. If it is if phi1 phi2, then actually 220 volt is induced. If you apply here 110 volt, then this lamp is full bright. But if the flux produced by coil 1 and coil 2 are opposite, then net flux here is 0. Then no EMF is induced. Then this is bulb is not bright. Then we can know this means their dots are opposite. Coils are oppositely connected. तो ये दो का हमें पता चल जाएगा. फिर हम the same process is apply for B and C. B and C को short करेंगे and we apply we put the lamp here. Then we know the polarity of coils. Okay, this is the identification of transformer coils or your three-phase motor coil terminal. Okay, with lamp. Okay, we apply the potential, then we can know. Okay. This is the identification of coil. Suppose newly motor is manufactured, we do the winding. Then how we put their polarity name? Okay, terminal identification. Or either a very old motor, their nameplate is deteriorated. Then how we will check the like their terminal identification. Okay, then we mark like this. Then so that we can never do mistake in the connection to make star delta. Okay. So like now we come to the capacitance. See their capacitors either they are in series, two capacitors, C1, C2. Okay. The inductor inductor series parallel is very important. There is a mutual inductance also sometimes, okay? But here capacitor or there is a two capacitor in parallel, C1, C2. So actually now, in case of capacitor, it is opposite to resistance. In series na, total equivalent resistance in series. Sorry, total capacitance. Total equivalent capacitance in series is like a parallel 1 by C1 plus 1 by C2. So, or CSC equals to C1 C2 by C1 plus C2 like this. Now if both are equal, C1 equals to C2 equals to C, equal value, then C square, and this become a 2C, then C is the power is cancelled, it is C by 2. Okay, please. 1. In case of parallel, so this formula is used in parallel, CP, total equivalent capacity, it is simply added. So it is opposite to resistance. Okay, in parallel it is simply add algebraic sum C1 plus C2. But now if C1 equals to C2 equals to C, then CP equals to C plus C, it is double. This is 2. So like capacitance, if now there is a question, it is asked in your examination, I show you. If two equal capacitor are in series, earlier it is asked in all DTO questions, please, here it is there. We can ask, see here, which has a, see this question, which has a greater equivalent resistance. Resistance means actually it is reactance. Okay, if two equal capacitor are in series or parallel, region. So if two equal capacitor are in series and parallel, then reactance. So see, this is not a reactance, it is capacitance. This is total equivalent to capacitance. Okay, this is also total capacitance, equivalent capacitance. Please. Now we come therefore total equivalent reactance of this circuit. Reactance means resistance, because reactance is unit is also ohm, resistance is ohm. Okay, that's why reactance or resistance. Okay, so see total equivalent reactance, you know, for series reactance equals to XC, but in series XC equals to 1 by omega C. Omega C. Now omega C is in series, total in series, it is C by 2, na? 1 by omega C by 2. Then this 2, it is 2 by omega C. This, please you write, this is a 3 equation. And here we calculate the total equivalent reactance. Reactance or resistance. Okay, please. So it is in parallel. This is the total capacitance. Then reactance is XCP. Yeah, reactance. You know it is omega CP, but P is double. So it is 1 by 2 omega C. This is 4th equation. Actually, total capacitance is more in parallel. Capacitance in capacitance unit is farado. So it is double of double, na, it is 2C. This is C by 2, it is come. But reactance is, see, reactance is, in which case it is high, in series it is high reactance. Now from equation 3 and 4. So if we divide na this reactance in series circuit to reactance in parallel, so it is this value is 2 by omega c, and this value is 1 by 2 omega c. So see, this is now we have changed na 2 omega c into 2 omega c by 1. Omega cancel. It is 4 raised to 1. Okay. It means, hello, in total capacitive reactance in series equals to 4 times of in parallel. So which is greater? This is greater, na? XCE is greater than XCP. Okay? Correct or not? Hello? This numerical we also solve. Please, if this question is asked, na, okay, this is the solution of this. Okay. Okay, please. Correct now? Let us we cover the series parallel of RLC also here. That's why it is required in one question. Now we come to our main question. Hello, here. Okay, please. What they ask?
सर ये लास्ट वाला एक बार रिपीट करना, ये जो जिसमें ये कैपेसिटेंस ज्यादा आई है उसकी पैरेलल की
क्यों आई है? देखिए, very simple na. Always you remember this formula for capacitor connection. In parallel resistance ka, you know, it is देखिए रेजिस्टेंस के लिए याद रखिए, इन रेजिस्टेंस ना, when two resistance in series, total equivalent resistance is R1 R2 R1 plus R2. But if two resistance in parallel, R1 R2, then what is the total equivalent resistance? We calculate na like this. This formula you know? Hello?
yes sir.
This but ये कैपेसिटर के केस में ना, कैपेसिटर के केस में अपोजिट है. This is for series and this is for parallel. That's why, okay, these are like cross. Please, कैपेसिटर के लिए अपोजिट है. So what is the total capacitance if two capacitor are in series? This formula. And for parallel, simple addition. First, we have calculated the total capacitance of circuit, parallel circuit. Here we calculate total capacitance of series circuit. So here it is come C by 2. If C1 equals to C, मतलब ये CC है, okay, like this. Then it is this. Here it is also CC. Then it is, means they are equal. C1 equals to C2. Okay. In this case, okay.
यहाँ तक हो गया सर क्लियर ना?
हेलो.
यस सर, यहाँ तक क्लियर हो गया है.
हाँ, उसके बाद ना हम रिएक्टेंस, जब आपको अगर टोटल कैपेसिटेंस पता है तो रिएक्टेंस का क्या फॉर्मूला है? अब हम रिएक्टेंस निकाल रहे हैं. ये दिस इज कैपेसिटेंस. 1 इक्वेशन एंड 2 आर टोटल कैपेसिटेंस. total capacitance of circuit. Now we calculate reactance. Now you know capacity, because it is now capacitive reactance is 1 by omega c. बस मैंने ये फॉर्मूला डाला है. P means is total equivalent parallel. P stand for parallel circuit के लिए, SC for series के लिए. तो देखिए लास्ट में हमने जो ये CSC की वैल्यू ये पुट किया C/2, तो ये हो गया. Here we put CP value is 2C, so it is 2. Okay. This
Okay,
is
sir, clear. Thank
now
you, sir.
we compare this two. How we can compare this? So we have divide equation 3 with 4. तो हमारे पास इसका मतलब ये रेशो निकाला मैंने इनका. If we calculate the ratio of series capacitive reactance of series to capacitive reactance of parallel. सीरीज के लिए आप SC लगाइए इसको, है ताकि कंफ्यूजन ना हो. सीरीज इन सीरीज, ओके. एस ओके, इट इज इन सीरीज है. टोटल कैपेसिटेंस इन सीरीज टू पैरेलल. देन वी फाउंड इट इज 4/1 मीन्स इफ यू कैलकुलेट ना CS raised to CP, their ratio, it is 4:1. इसका मतलब this is 4 times more than CP, correct ना? इसका कहने का मतलब है कि if we take a two similar value of capacitance and we connect in parallel or we connect in series, then which has a high reactance, or okay. In series it is high, 4 times more than parallel. वैसे भी सीरीज सर्किट में रेजिस्टेंस हाई होता है ना, एक्चुअल में देखा जाए तो. ओके, दैट्स व्हाई we operate the equipment means appliances in parallel in domestic. Okay.
सर अगर पूछ रहा था कि कौन सीरीज में कैपेसिटेंस ज्यादा होगा या पैरेलल में कैपेसिटेंस ज्यादा होगा, तो फिर उल्टा हो
then
जाता है ना.
opposite. Yes, correct.
ओके.
This, yes, you're correct. Please. Capacitance is different, reactance is different. Yes. Okay. Now we coming to our question. Please.
क्वेश्चन रिपीट करेंगे. अभी आपने क्या पूछा था सर से?
ये पूछा है कि अगर वो पूछते थे, यहाँ पर उन्होंने रेजिस्टेंस पूछा था, विच सर्किट हैज ए हाई रेजिस्टेंस. बट अगर दे आस्क विच कैपेसिटेंस, विच सर्किट हैज ए कैपेसिटेंस, विच मीन्स टोटल कैपेसिटेंस इन सीरीज और पैरेलल. तो देखिए कैपेसिटेंस हाई है in parallel, high capacitance because it is double, but reactance is low. Okay. You take an example. Suppose two capacitors, two capacitors. They are of 1 microfarad, 1 microfarad. So total is in series. What is the total capacitance? It is C1, C2 by C1. Okay, C/2, no? So it is half farad. But in parallel, if they are connecting like 1 micro or microfarad, suppose generally actually microfarad unit is there. So if you take a 1 microfarad, 1 microfarad, then total in this it is half, no? C/2, no? Here in parallel, C/2 means C is 1 farad each value. Okay, so it is 1/2 microfarad total. But here in parallel, okay, in parallel means suppose this and this 1 microfarad capacitance are connected in parallel. Suppose 1 microfarad, 1 microfarad. Then total capacitance in parallel is double of each value. This, okay, it is 2 into 1 means 2 microfarad. So capacitance is more in parallel 2. Here it is half, means 0.5. Okay. But if we calculate their reactance, now it is a total equivalent capacitance. Now we calculate total reactance. Total reactance. Xc equals to 1 by omega c. No, Xc equals to omega c. So if we put this value 1 by omega is 2 pi f. This is the same value, omega. We can write it is 0.5 omega, and Faraday microwave 10 raised to power minus 6 also. This is in Farad. Okay, minus, but it is omega into 0.5. This. It is a 2 into 10 raised to power minus. तो बताइए which is greater? Omega is same for both. This is less, because it is divided by 2. Okay, this is high. Okay, got it? Very simple. Means capacitance, this is higher, but this is low. But reactance is opposite. Okay, it is like saying that. Now we come to the question, please. Here we put the values here, this circuit. Hello. It is given 15 ohm. This is 0.1 Henry. This P1 is 2 microfarad. Then R2 is 10 ohm. This is 0.2 Henry. This is 0.5 microfarad. So basically, this is now here, suppose you apply voltage and frequency again. Now RR are in series, LL we add CC. So total resistance is, it is just series, so add. Okay, R1 plus R2. It becomes 25 ohm. Then total reactance, equivalent reactance, the 2 are in series. Then inductor or okay. Henry, this is 25 ohm. Then you come to capacitance. Now capacitance in series, hello, total equation. This, please you calculate, hello, total
0.4 microfarad.
0.52. So it is 2 into 0.5 divided by 2.5. Yes, 0.5, sorry, 0.4 microfarad. C, I think C is come. Now this is become perfect RLC. Now it is R, L and C. It is 0.4 microfarad. Okay. Then if you apply here potential, suppose AC with voltage and frequency. Now he said that, what is the question? He asking the frequency at which your circuit is resonant. Now you know na R and C. So what is the, we have drawn na this formula. Okay, this is the frequency of resonance. F equals to the frequency at which above circuit is resonant. Circuit is resonant. Okay, F naught equals to 1 by 2 pi under root LC. Now L and C you know. So please F naught equals to 1 by 2 pi under L is 0.3. Okay, into C is 0.4. Please you multiple with also. Micro is 10 raised to power minus 6. So for easy calculation, what you do? We can do
we square the both sides, then it will be very easy.
Square, yes. F square equals to 1 by 2 into pi means 3.14. So this also is square. 1 ka square is 1 only. And this is simply, now root is removed from this side. So it is become 0.3 into 0.4. But my dear, we take this is above, then it become a plus. Okay. Now we can solve this. F naught square equals to what we get? 0.4 into 0.3 into first you calculate here this 2 into 3.14, then square of this into 0.3 into 0.4. This we get. Then inverse into 10 raised to power. It comes, this value comes to 11299.98. This much. Then if we remove this square, then it is root of this 211,299.98. The root of this
459.6 hertz.
very good, 459.67 hertz. So this is the frequency at which this circuit is come at resonance. Okay. So here actually they are given you have to calculate their equivalent. We reduce this circuit to this. Then we apply this formula. Okay. First we calculate total resistance, total inductance, then total capacitance. That's why I explained this series parallel also here. Okay. Okay. So you have a nice day. Now only we solve the questions, and now this chapter is mostly finished. In the evening time, we solve the remaining questions. Okay, for fundamental. But nowadays, every year every month there is a question from like this AC/DC circuit. Okay, parallel resonance question was also asked last month. Parallel resonance. So in evening, means in evening session, I will show you the parallel resonance also. I explain. Okay, parallel
Sir,
resonance.
sir, can you please explain the point number 8 in difference between series and parallel resonance circuit?
ग्रुप में डाला है हमने, देखो चलिए तो
Yeah, I have seen, but can you explain the point number 8?
पॉइंट नंबर, अच्छा ओके पॉइंट नंबर 8 ना, सीरीज रेजोनेंस यूज इन ट्यून सर्किट टू separate the wanted frequency from incoming frequency by offering low impedance. Several used to present a maximum impedance. Actually, it is an application of series and parallel resonance. Series resonance is used where have with your minimum impedance. So it is low impedance for that tuning frequency. Incoming frequency at we require a low impedance. In that circuit it is used. But parallel resonance,
it is separating the wanted frequencies or unwanted frequency?
It is separate the wanted frequency. It is separate the wanted frequency. No? Wanted means separate the wanted. Yes. So actually, suppose incoming frequency in a wave trap, na, like in communication lines. If we put a resonant, then it pass only the wanted frequency. That's why it is mentioned at a bit. It separate the wanted frequency. Okay. After resonant circuit, only we get a wanted frequency. Other it is block, no? Like that. Okay. Good day.